Okay, so this is the review session for EGME 417 and spring 2023 for midterm 2. Okay, so for midterm 2, we only had two homeworks that are associated with this midterm. And so the first homework is homework 4, and so that has to do with time marching schemes. Okay, and then homework 2 was about diffusion with finite volumes. So I wanted to review both today. Okay. All right, so let's start with time marching schemes. Okay, so time marching schemes, this has to do with problems that are naturally unsteady, okay? And what unsteady problems mean is that these are problems that change with time. Okay, so how do we know things are going to change with time? Well, these are problems that have a time derivative in its governing equation, right? So we have a partial phi, partial, okay? Okay. And so, we want to solve these using our usual computational methods, but we have to treat time a little bit differently. So that's kind of the whole theme with this whole section here is that because time behaves differently than space, we need a new collection of methods in order to solve this. Right, and that's what the time marching schemes are, right? And so the time marching is basically how we solve these types of problems with time. Okay, we're still going to rely on our kind of our fundamentals of finite differences, and so that stuff's not going to change. It's just how we apply them and how we actually transform them into equations. That is going to be different. Okay. Okay, so the first method that we went over was the explicit Euler method. So we went over two main methods, and so explicit Euler being one and implicit Euler being the other one. So we'll review both in this video. Okay. So the idea with explicit Euler is that this gives us, we want to have an explicit expression for solving for the solution at the next time step. Okay. Okay. And so what do I mean by explicit, right? So whenever we have any kind of time marching scheme, we're solving for the solution at the next time step. Okay. Okay. The next time step being n plus 1. Okay. Right. So essentially, what we want to solve for is this, right? And so an explicit expression for phi n plus 1 means that phi n plus 1 is going to be by itself. That means it has to be the only n plus 1 term in the entire algebraic expression. Okay. right? Because if there's only one n+1 term, that means that, then we can solve for it outright. We don't have to kind of combine it together with other equations, right? That's what implicit U is going to do. Okay. So, on the exam, you won't have to derive any kind of expressions like this, but it's useful to kind of to look at it just to see kind of where it comes from, right? So for explicit Euler, let's start with the 1D equation. So the 1D equation is partial phi partial t is equal to minus u partial phi partial x plus k partial squared phi partial x squared plus q of x. Okay. Now let's replace every single expression here, or every single derivative, with the finite difference expression, right? So first we have the time derivative, and so we have phi n+1 minus phi n. Both of these are evaluated at the node I. Okay. So that's how we do the time derivative. And so we do basically a forward difference in time. So we use the superscript, the n and the n+1. This is equal to minus u phi n+1. And I'm just going to use a central difference for now. Okay. Phi I+1 minus phi I-1 divided by 2 delta x plus k phi I+1 minus 2 phi I plus phi I-1 divided by delta x squared, okay, plus q of xi. Okay. All right. So this is kind of what we have here after we apply our finite differences to all the derivatives. Okay. The main thing that you should see here, or the main thing you should focus on, is that for the derivatives on the right-hand side, or our space derivatives, we don't have any time indices assigned to these yet. Okay. So for all of these phi terms here, okay, all 5 of these, we need to assign either n or n+1 to these terms. Okay. And then depending on what we choose, that's going to lead us to either the explicit Euler method or the implicit Euler method, right? So for explicit Euler, remember we only want to have one n+1 term for the entire expression. So we're just going to choose n for all of these. Okay. All right, so let me go ahead and write n. And for all of these phi terms here, okay? Then what I'm going to do here is I'm going to isolate the n+1 terms on the left-hand side. And because we assign n to everything else, we should only have one n+1 term. Okay. Okay. So I'm going to skip the details of the algebra just because this is a review video and we only have a certain amount of time. Okay. But in the end, you get something that looks like this. We have bi n+1 is equal to u delta t divided by 2 delta x plus k delta t divided by delta x squared times phi n-1, or excuse me, I-1 to the n, okay, plus 1 minus 2k delta t divided by delta x squared phi to the n, okay, plus minus u delta t divided by 2 delta x plus k delta t divided by delta x squared phi+1 and n plus q xi delta t. Okay, And so what we have here is an explicit Euler expression for 1D convection diffusion. Okay, and so this equation here, it is important. So if you were to apply this directly to an interior node, you can use this equation just fine. Okay? But the feature that I want you guys to focus on here is that we have an explicit formula for phi n plus 1, right? At least for this node I. And so for this node I, if we wanted to solve for the solution at the next time step, then we could use this equation here and we'd be able to solve it outright. Okay? Because the assumption is that everything on this side of the equation, everything on the right-hand side is known. Okay. And that includes the current solution. And so that includes the solution phi at time step n, right? And so that is the solution at the current time step. And so remember, we are going to assume that we know that, okay? And so if we know that solution, that means everything on the right-hand side is known. That means we only have one unknown in this equation. And so we can solve just this one outright, okay? And so it's going to be different. And so when we compare this to the implicit Euler is going to have more than one n plus 1 term in this expression. And so, we're not going to have this explicit kind of equation for that. Okay? Because technically speaking, we can solve as, assuming we know everything on the right, we can solve for the solution at the next time step for each node individually. And so we actually don't need to solve them together with the other nodes, which is something that's quite unique. Okay. And so from explicit Euler, you basically get a situation where, because of your explicit expressions, you can have, all that's required to solve these is just matrix multiplication. Okay. Okay. All right. And so you probably seen me use this expression before. Right. And so under explicit Euler, so this goes for both 1D and 2D, in order to get the solution at the next time step, you would take a coefficient matrix A, where the entries of that matrix are given by these expressions here. Okay. They're circled in rainbow for some reason. Okay. And so those expressions there are going to give us a matrix, right? But unlike our usual matrix that we use, and we use that matrix to invert, for explicit Euler, we actually multiply that matrix by the current solution. Okay. And this ends up being a lot cheaper. Okay. And so if our coefficient matrix was on the left-hand side, like it usually is, you would have to either invert that matrix or you would have to solve the corresponding system of equations in order to solve for its value. But since the matrix is on the right, and it's multiplying by something that we already know, which is the current solution, the only thing you just need is just matrix multiplication in order to get this to run. Okay. And that is much cheaper. And so, whenever you can avoid matrix inversion, whenever you can just do matrix multiplication, this is always going to be a lot cheaper. Okay. Cheaper meaning that, it's going to take a lot less time to run. But of course, there's no such thing as free lunch, both in computational work, also in life. Okay. And so, if you're going to be paying less, essentially, if you're going to be waiting less for the result, you're going to get a result that's of similar quality. Okay. And so for unsteady problems, the concern that you have a lot of the time, especially for explicit problems, is that their solution may become unstable. So that's kind of the risk that you run. Okay. All right, so I want to do a quick example here. I'm not going to go through all the details of it just because it's in the notes, but I did want to kind of show you kind of how to apply this, especially how do we actually apply this to advance the solution forward in time. Okay. Okay. And so our example is the following. So we have partial phi, partial t is equal to 3, partial squared phi, partial x squared. Okay. And so this is a simple unsteady diffusion problem, right? Our boundary conditions. Okay, our boundary conditions are the following. And so we have a Dirichlet boundary condition on the left. So we have phi of 0 and time is equal to 1. And then we have a Neumann boundary condition on the right. So d phi dx at x is equal to 1 and all times t is equal to 2. Okay. All right, so we also have an initial condition. Okay, so for our initial condition, we assume everything's going to be 0. So you have phi at x and 0 is equal to 0. Okay. And so we want to advance the system forward in time using explicit Euler. Okay. And so what I'm going to do is I'm going to apply this equation up here, okay, for all the interior nodes, and we're going to have similar equations for the boundary nodes as well. Okay. Okay. So for the interior nodes, oh, I should also say that we're assuming that we just for now, for this example, we're going to have a 5 nodes in our grid. So for interior nodes, apply our equation above. Okay. And so by equation above, what I mean is this equation up here. Okay. And so for this particular problem, we have a velocity of 0, so u is equal to 0. Delta t is, I didn't give it to you, and delta x I didn't give it to you either, but we do know k, okay? And so we can plug in for this and get all the coefficients in that expression, okay? So let's assume delta t is what? Delta t is 0.1 seconds. Delta x is equal to 0.25. Okay, and so we plug that in. What we get is bi n plus 1 is equal to 4.8 bi minus 1 and plus 1 minus 8.6 bi and n. Sorry, this should just be n, not n plus 1. Plus 4.8 bi plus 1 and n. Okay. Okay, so for a 5-node grid or 5-node mesh, our 2 or 3 nodes in the interior, nodes 2, 3, and 4 are our interior nodes. Okay, so we have I equal to 2, I is equal to 3, I is equal to 4. Okay, so this we have 4.8 v1 n minus 8.6 v2 n plus 4.8 v3 and n. Okay, and so on and so forth for the other nodes as well. Okay. So those are all our interior node equations. Okay. Okay, and we also have our boundary condition nodes. And so for I is equal to 1, on the left-hand side of the domain, we have a Dirichlet boundary condition. So this was actually pretty easy. So P1 n plus 1 is equal to 1. Okay. Then for I is equal to 5, we have a Neumann boundary condition. So Neumann boundary condition states that d phi dx, in this case, is equal to 2. Okay. So let's plug in our normal forward difference applied at node 5. And so we have phi5 minus phi4 divided by delta x is equal to 2. Okay. Right, so here's where things get a little bit tricky because remember, we want to have an n plus 1 in this expression, but we only want to have one n plus 1, okay? Since we're on the n is equal to 5 equation, okay, that means we should put the n plus 1 on phi5, right? Because this is 5's equation, so there should be a phi5 n plus 1 in the expression, okay? And since we only want one of these, that means the other phi term, phi4, is going to be given the superscript n. Okay. And so from this, we get the following equations. We have phi5 n plus 1 is equal to 2 delta x plus phi4 n. Okay. All right, so let's go ahead and put these into matrix form. Okay. So you have phi1, phi2, phi3, 4, 5, right? So all this is the left-hand side. So that's going to be n plus 1, okay? Then we're going to write a matrix here of coefficients for the phi n terms, okay? So every term with a phi n, we're going to write a coefficient for that. So our first equation here is going to be phi1 n plus 1 is equal to 1. That means the coefficient for phi1, in this case, is 1. Okay. Everything else is 0. Okay. So this is multiplied by phi1, phi2, phi3, phi4, phi5, all at n. Okay. All right, so for row 2, these are one of the interior nodes. We have a 4.8 minus 8.6, 4.8, 0, 0. Okay. All right, and then finally, for the last row here, we have a Neumann boundary condition. And so for a Neumann boundary condition, we only have one coefficient here, which is the phi4, which is 1. Okay. Okay. So that's the matrix of coefficients multiplied by phi n. Okay. To this, let's add the extra terms here. Okay. So everything on the right-hand side that's not a phi n term, we're going to put in this extra vector here. Okay, so most times that's going to be the boundary conditions, but if you have a source term, this is where it would go as well. Okay. Okay, so for the first row here, we have phi1 is equal to 1. I'm so sorry. So the first row in the matrix here, because we don't have any phi n's for this equation right here, we only have the phi n plus 1. That means this coefficient here is going to be 0. Okay. So that was kind of a mess up on my part. So for this entry in the matrix right here, this top left one, for explicit Euler is just going to be 0 because we don't have any phi n's in that expression, right? And so if you look at our equation here for phi1, okay, we only have the phi1 n plus 1 for n plus 1, but we don't have any phi n's in this expression, okay? Okay. But what that extra 1 does is that it comes into this kind of vector on its own, right? All right, so for the 3 interior nodes, we don't have anything extra, so all those would be 0. And then for the last one, I is equal to 5 equation, we have just a 0.5, which is the result of 2 times delta x. Okay. Okay, so the reason I'm kind of reminding you how to put this in matrix form is, I want you guys to know kind of how the time advancement happens. Okay, so for the first time advancement, we're going to plug in the initial conditions in for the phi n's. Okay. So that means everything on the right-hand side of the equation. So all of these in right here, right? So this is a matrix multiplication, and so we're going to multiply that matrix by whatever our current solution is, okay? And so our initial conditions assume that these are all equal to 0, right? And so we plug in zeros for all of these. Okay. Okay, so we're going to plug in zeros because that's our initial condition. Right? Then we're going to multiply that through, and then add that together to our forcing vector on the right, and so that's going to give us our first solution after the first time step. Okay. 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 Okay, so after the first time step, it's actually pretty simple. And so, we have just a vector of zeros. We're going to multiply that through. And so that's going to cancel everything there. Okay. And so the phi okay, after one time step, and so I'm going to put a 1 here. Okay. After one time step, our solution looks like this. We have 1, 0, 0, 0, 0.5. Okay. And so to advance this by one more time step, what we're going to do is we're going to take this and plug it into phi n's, or the previous spot where we had phi n's, and then just carry out the same calculation. Okay. So we're going to put this up here. Okay. And so for step 2, we come back up to this equation right here. This would be a 1 and a 0.5. Okay, because that was what we found from the last time step, and then we carry out the same calculation as before. Okay, and so if a problem asks you to solve for the solution after the first 2 or 3 time steps, that's essentially how you would do it. Okay, most of the time you're going to start with 0, and so that part is okay. But then just remember, you kind of need to repeat the process, but replacing the current solution with what you previously found. Okay. Okay. So that's explicit Euler, and so that took quite a while. So let me review implicit Euler just kind of very quickly before we move on, and then we'll move on to diffusion with finite volumes. Okay. So implicit Euler. Okay. So for implicit Euler, this is a situation where instead of applying n to all the other phi terms, we're going to apply n plus 1. Okay? And so for the all the space derivative terms, the convection and the diffusion, we're going to apply a time index of n plus 1. Okay. Okay. And so if we do that, then it looks something like this. Okay. Plus q, can't forget q. Okay. So that's our normal expression there for the for our conservation equation. So this is just after we applied finite difference to the entire equation. And so what we're going to do now is that instead of applying a time step of n to all those terms, we're going to apply n plus 1. Okay. And so after we do that, we're going to apply the same strategy. So all the terms of the n plus 1, we're going to move over to the left-hand side, and all the terms with n, we're going to keep over on the right. And this is going to have one very important consequence relative to explicit Euler, and that is that we can no longer say that we have just one n plus 1 term. We're going to have multiple n plus 1 terms. Okay? Okay. And so we don't have a situation anymore where we can explicitly solve them. But we can still solve it. It's just going to be a little bit harder than before, because now what we have to do is we have to solve all of the basically all of the implicit Euler equations for all nodes together at the same time. Okay. Okay, and the main mathematical technique that we use for this is basically solving a linear system. So basically our backslash operator, or another way that you can say is that it is our matrix inversion. Okay. And so what we get with that is the following expression, right? And so again, I'm going to skip all the details, but you can see all the details in the notes. Okay. And so for 1D implicit Euler that involves convection and diffusion, you have minus u delta t divided by 2 delta x plus, or excuse me, minus k delta t divided by delta x squared vi minus 1 n plus 1 plus 1 plus 2k delta t divided by delta x squared vi n plus 1 plus u delta t divided by 2 delta x minus k delta t divided by delta x squared times vi plus 1 n plus 1 is equal to vi n plus q of xc delta t. Okay. And so just like the explicit Euler expression, we would basically take this and we'd apply it to all of the interior nodes. Okay. And so of course, for this review here, I only went over 1D, but for 2D, you would apply the exact same methodology. And so there's really nothing new in 2D. Okay. Okay. And so with that, let's go ahead and move on. And so, we spent a fair amount of time on unsteady problems. Let's go ahead and talk now about finite volumes. Okay. Okay. Sorry about that. I had to run to the restroom real quick. Okay, so let's go ahead and review diffusion with finite volume. But first, we have to review what finite volumes are just in general. Okay, so finite volumes is kind of a whole new technique. So that's kind of the whole theme of this midterm is that we're learning new techniques, whereas kind of the first midterm we were applying the same finite difference technique to basically every different kinds of problems. So finite volumes is kind of an alternative to finite differences. It's a little bit different than unsteady problems. Unsteady problems, that the nature of the problem was different, so we had to use a different kind of technique because the nature changed. But for finite volume problems, it's really a different method to accomplish essentially the same thing as finite differences. Okay. The big difference here is that in finite volumes, we're concerning ourselves with the cells that are defined in the grid rather than the grid points. Okay. Okay. So we have a typical 2D grid like this. Okay. Okay. Normally for finite differences, what we're solving for is we're solving for the solutions at the intersections of the line. And so I call those the nodes or the points in the grid. Okay. For finite volumes, we're actually interested in solving for the solutions over an entire cell, right? And so over something like, I have a highlighter, like that, right? And so we're interested in, what's the solution inside the cell? What's the solution inside this cell? Okay. So on and so forth, right? And so to do this, because now we're looking at a solution that's kind of valid over a region of space, that kind of opens up some new mathematical tools for us. And that mathematical tool here is integration. And that opens up, some new things for us. Okay. I'm going to skip straight to the 2D stuff because I think finite volumes is, and I think 1D is necessary just to kind of just to build up the theory. But where it kind of really gets interesting is in 2D. Okay. And so we're going to start with diffusion, and then, of course, at least right now, as of right now in the class, we're kind of in the middle of applying this to convection as well, right? And so for diffusion, okay, and so for diffusion in 2D, we end up with something like this. And so our governing equation in vector form is given by the following. Right, so this is the vector form of our diffusion equation, right? So what I'm going to do is I'm going to integrate this equation over the area of a 2D cell. Okay. Okay. And so once we do that, we can take this integral on the left-hand side and we can convert it using the divergence theorem. Okay. And so on the left-hand side, what we have is minus k line integral of gradient to phi dot product with n ds. Okay. And on the right-hand side, what we have is we're going to apply trapezoidal rule to evaluate this integral. Okay. And so this becomes qxc yc times delta x delta y, right? Where xc and yc, those are the coordinates of the cell center, right? So visually it looks like this, and the visual is kind of key here for finite volumes. Okay. So here's a typical finite volume cell, and so it could be, one that we've highlighted up here. I'm just kind of blowing it up big here. Okay. Okay. The horizontal length of the cell is delta x. The vertical length of the cell is delta y. Okay. And the centroid of the cell is xc and yc. Okay. Okay. And so when we integrate this, or when we perform a line integral around this entire cell, basically what we're doing is we're going around just like this. Okay. And so we're integrating basically just around the perimeter of the cell, right? And so one thing we can do is we can label each side of the cell here. So I usually call this the east face. This is the north face, the west face, and the south face. Okay. And so what we usually do is we break up this integral into each of those different, each of those different sides. Okay. Right. And the other thing that we have to do is we have to take our integrand. So our integrand here is the gradient of phi dot product with n. Okay. Okay. And what we have to do is we have to evaluate this on each side of our cell. Okay. And so let's break this apart, because it's essentially just a dot product. It's a dot product containing two kind of things that look a little bit scary, but it's essentially just a dot product. So the gradient of phi, this is nothing more than the vector partial phi partial x, partial phi partial y. Okay. And n here, this is the normal vector on that side. Okay. So we've talked about the normal vector a couple times in this class, but the normal vector is just a vector that points outward from the cell perpendicularly from that side, right? So on the east side, it points to the right. On the south face, it points down. On the north face, it points up. And on the west face, it points to the left. Okay. 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 And so when you take the dot product of these, you're going to get different, different expressions for each side of the cell. Okay. Okay. All right. So let's go ahead and plug in for that. Okay. All right. And so our entire line integral here is minus k times integral partial phi partial x. This is on the east face dy, okay, plus integral partial phi partial y dx on the north face minus, right? So the minus sign comes out here because of the normal vectors that point in the opposite direction, okay? Minus integral on the west face partial phi partial x dy minus integral on the south face partial phi partial y dx, okay? Okay, so I'm bringing this form up because this form here is going to be useful for us when we apply our boundary conditions, okay? All right, and so for each of these integrals, we've simplified these integrals as much as we can. And so the next step here is to apply a trapezoidal rule to evaluate each of these integrals, okay? Okay, and so if we apply trapezoidal rule, we get partial phi partial x evaluated at the middle of the east face, delta y, plus partial phi partial y evaluated in the middle of the north face, delta x, minus partial phi partial x on the west face, delta y, minus partial phi partial y on the south face, delta x. Okay. Okay. So this right here is an equation worth boxing because we have different form. These expressions here are going to take different forms depending on if we have a neighbor on that side or not. Okay, and this is where things get tricky with finite volumes, because with finite volumes, the way you apply the boundary conditions is going to be different. Okay, because it's the way we apply boundary conditions is different. Because in finite differences, remember, we apply boundary conditions by making those boundary conditions an actual equation. In finite volumes, our boundary conditions are going to modify this expression. Okay, most notably, the boundary conditions are going to modify each of these kind of derivative terms depending on what's on the other side. Okay. Okay, so there are three kind of cases here, and so I'll go over what those three cases and kind of what you should plug in for each of them. Okay, so the most common case that you're going to see is that this cell is bordering another cell, so there's another cell on the other side of that face, right? And so for instance, for the east term here, if there's another cell on to the east of this one, then we can use this expression, okay? Okay. So case one, another cell on the other side. Okay. And so the case where you have another cell on the other side, we can plug in an expression that utilizes that other cell's center, okay? Okay. And so in this particular case, we're going to use a finite difference expression that utilizes that other cell's value. So for instance, partial phi partial x on the east face is equal to phi sub big E minus phi sub c divided by delta x, okay? Let's do one more example. On the south face, we have partial phi partial y on the south face is equal to phi sub c minus phi sub s, all divided by delta y, okay? Okay. And so if there's another cell on the other side of that face, then you're just going to use that cell center value in your expression, okay? Okay, case two. Case two is if we have a Dirichlet boundary condition. Okay. So let's say that this cell is on the edge of the domain and it's on a domain side that has a Dirichlet boundary condition, okay? So in this case, we're going to use a finite difference expression. A finite difference expression that incorporates that Dirichlet value okay? It incorporates the Dirichlet value and uses half of the cell length. Okay. And so for instance, let's say we have partial phi, partial w, or partial phi, partial x on the west face. Okay. And so we're going to have phi sub c. Okay. So there's no west neighbor, and so we can't have a phi sub w, but what we can have is the phi sub 0. So this phi sub 0 here, this is what I'm using for the Dirichlet value. Okay. And we're going to divide this by half the cell length. So it's going to be delta x divided by 2. Okay. All right. And so the third condition here is if we have a Neumann boundary condition. Okay. This is the easiest case. And so in this case, what you're going to do is you're going to replace the entire derivative expression with the Neumann value. Okay. And so let's say we have partial phi, partial y on the north face. Okay. You're going to set that equal to gamma. Okay. Okay. And so those are the three cases that you have to do, and you have to apply this to all 4 integrals for each cell. Okay. And so you're going to do that for, you're going to do this basically 4 times, right? Okay. And so once you apply this to all 4 of those derivative expressions, essentially what you've done is you've evaluated all 4 of the finite volume integrals, okay? And then once you do that, you just kind of combine them all together And then that combination is going to give you the algebraic equation for that set. Okay. So that's about all we have time for. And so, there's of course more detail for this in the notes, but I would say this is kind of the most important information to review for the midterm. Okay. If you have any other questions on the midterm, you're definitely free to come and contact me. I'm always always open for questions. I know we have one more office hour or two more office hours technically before the midterm exam, but if you have more questions before that, don't be afraid to email me. We can set up an appointment to meet beforehand. Okay. All right, so best of luck studying, and I will see you guys in lecture soon.